Welcome everyone to the second presentation in the series, Forging Ahead. The title is, as you can see, That Heavens Do Not Fall, Gödel's second incompleteness theorem and the consistency of arithmetic. I have decided to start this lecture by talking some about the grand history of the subject before launching into the materials. But I will again say, this incompleteness theorem is oft taken as the greatest theorem of all time by at least some people. So, I brought here, by special arrangement from the library, our copy of the original Whitehead and Russell Principia Mathematica. It is not allowed to circulate. I had to sign a special form just to show it to you here. We see it's a big bunch of stuff, and this was basically Bertrand Russell getting mathematics back on its footing after his great paradox of the last lecture. Now, the next volume that I have here for your display is this thin little volume, a fun one, Edmund Landau's Foundations of Analysis. It shows how you can take just the piano axioms, some rules of inference and common notions, and elementary set theory, and build up all of conventional mathematics off those 5 axioms. Quite a marvelous production. Very important to today's lecture is this volume, Kurt Gödel's collected works. This is the source. Kurt Gödel himself translated into English for the likes of me and others. Now, this next one is by Joseph R. Schoenfeld, entitled simply Mathematical Logic. Now, we have a bit of an history here. Gödel, of course, has this huge reputation. Kurt Gödel was at the Institute for Advanced Study at Princeton. Joseph R. Schoenfeld got his doctorate at Princeton. They were there at Princeton at the same time. Do you think they ran into each other? Most likely. So Schoenfeld was getting a lot of his logic off of Gödel himself. And yours truly was getting his logic from Joseph Schoenfeld when he was a graduate student, that is myself, at Duke University. So I had a front row seat to this material and didn't even know it at the time. Straight from Joseph R. Schoenfeld. Those who know the name know it's a big name. Sitting next to me was Richard Gödel, who is author of this book titled An Introduction to Mathematical Logic. I was there as a graduate student. Dr. Gödel was faculty. Schoenfeld's reputation was so high that this other faculty member was sitting in the room taking notes and produced this version of mathematical logic, which is much more readable than Schoenfeld's, which is notoriously dense and hard on the reader. So if you wish to learn traditional mathematical logic, I recommend the Gödel even over the Schoenfeld, but they're both good to have. Now, this great theorem was presented to the general public by Douglas R. Hofstadter. We see here in year 1979 in this book, Gödel, Escher, Bach, and Eternal Golden Braid. This book is thick. It's a bit prolix. It goes off on many tangents and digressions. However, it presents the theorem correctly. It gets it straight. You will not be led astray if you should read the Douglas R. Hofstadter book. I wish I could say the same about this book, but I cannot. It is by Morris Klein and is entitled Mathematics, the Loss of Certainty. Morris Klein has an excellent reputation as an historian of mathematics. His magnum opus is on many mathematicians' bookshelves. It is used as a reference. Dr. Klein was just wonderful at history. Morris Klein wrote about the incompleteness theorem, and he had a totally doom and gloom attitude towards the whole thing. And I'll just go tell you this story because it's important. I was there at a math conference of logicians, dreadful to think, a bunch of math logicians in a room and waiting for the presentation to start, and sitting next to me was Dr. Gödel. And I said to Dr. Gödel, oh, no one of my generation worries over the consistency of arithmetic. And someone from behind me, in the row behind, tapped me on the shoulder and said, oh, I have spoken with Morris Klein. I tried to set him straight, but couldn't. So the purpose of this presentation is to set the record straight, get things going correctly. And this theorem is worth all the labor we are doing just to present it, and the proof is far beyond what we'll do today. Now, the next thing to talk about is this Derek Muller and others' Math's Fundamental Flaw, originally called Math's Fatal Flaw, hit YouTube on year 2021 on the Veritasium channel. Similarly, Veritasium has excellent episodes. I often tell people that this is the best presentation of mathematics and science for the general public of the current age. And of course, I think it will stand the test of time as well. However, wonderful though the Veritasium channel may be, it's not flawless. I can tell that this book by Morris Klein is the source behind this episode of Veritasium. I can tell that as easily as English professors say, oh, this is the source of the play Othello. You just see it, you just know it. So this problem was perpetuated into the Veritasium episode, and now the Veritasium episode has 25 million views and counting. So you can see, as a mathematical logician, I am not willing to just sit idly by while misconceptions are erroneously perpetuated in our profession. I am here to set the record straight. Now, I am going to, at this time, talk about this book, which is different from the others. First of all, it's by myself. I'm the author. This is what I had promised in the first presentation, that I will take mathematical logic and use it to create a user-friendly, but still machine-parsably rigorous formalization of the material. But that's for later presentations. This is the first edition. I'm working on improvements to the second edition. I need to get those to the publisher soon. Second edition should be coming up. The first edition is very, very good, incidentally. It's got a lot in it. So, with all this as prelude, let's move to our material. We review the division between ground-level mathematics and meta-mathematics. Not understanding this division is behind all the misconceptions of the incompleteness theorems. So once you understand this, everything makes sense. This division, as shown last time, is absolutely necessary to prevent Russell-type paradoxes from arising. The ground language is machine-parsably rigorous and formal. You can take symbol strings, send them to a properly programmed computer, and the computer will tell you whether it parses or not. It has the familiar operators of for all, for some, if then, if and only if, and or, as we've seen last time, negation, and backslash, the last of which performs substitutions. Now that the first presentation is done, we can now say a statement is formed in the ground language by taking atomic statements. Give yourself some atomic statements, a whole bunch of them. Now put them together with these operators, close up, and the set of everything you can create is this set of ground level statements. That's all the ground language. Above the ground language is the meta language. We like to think that the meta language is above, but maybe it's across or below. The meta language is in English for people who speak English, and French for those who speak French. It is decidedly not machine parsably rigorous. It is needed to speak of ground-level mathematics in order to avoid Russell-type paradoxes. It is needed to do mathematical logic at all. This division will come even further into play as we get into things. Now, we have this cause for pause. A contradiction in the midst of a proof by contradiction causes the assumption that led to the contradiction to be proof false. But a contradiction proved out in the open causes an entire branch of mathematics to go into a state of contradiction or chaos. Is arithmetic free of such contradiction? If so, we say that arithmetic is consistent and 2 plus 2 is indeed 4, which is a very prevalent opinion. But if arithmetic is inconsistent, then 2 plus 2 can be proved to be 4, it can be proved to be 5, and it can be proved to be 27. I hope everybody is rooting for the consistency of arithmetic. And many people have never until now even thought that arithmetic might be inconsistent, but this has been a concern for some people. Now, the contrapositive of the cause for pause is the reason for hope. If there is even a single statement in the ground language of arithmetic that is so false that it can be known that there cannot ever be a ground level proof of it, then all of arithmetic can be known to be consistent. I'll let those people pass back and forth and see that is the contrapositive of the cause for pause. So, let's go to the highest authority on these matters, Gödel himself. One thing about Gödel is how to pronounce his name. It took me years to figure out to get this to happen. Say Gödel, Gödel, as if there's no umlaut there. Then move the tongue back in your mouth some. Gödel. Once you find that vowel, say it over and over again till you can say Gödel all you want. You can also say Goethe and other umlauts whenever you encounter them. But it did take me a while just to find that vowel, but once I found it, I made sure never to lose it. So, here's Gödel himself in 1929 and 1930. If to the Peano axioms we add the logic of Principia Mathematica with the natural numbers as individuals, together with the axiom of choice for all types, we obtain a formal system S for which the following theorems hold. Thus, S is Peano arithmetic. Arithmetic, as we call it in math jargon, and it's beefed up with some rules of inference to make it a whole logical system. So S is pretty much arithmetic. His first thing that he showed, we now call it the first incompleteness theorem. The system S is not complete. That is, it contains propositions A, for which neither A nor its negation not A is provable. I put that in bold and the rest in lighter type for purposes of this presentation. The stuff in lighter type is just as important, fascinating, and interesting, but I'm focusing on what's in bold. So, the system S, Peano arithmetic, has in it propositions A, so that there's no ground level proof either of itself or of its negation. If ground level proof is all you have, then you'll never know which one it is. And that's quite an assertion, and in the first presentation I went over some consequences of that. But today we're on the second incompleteness theorem. Even if we admit all the logical devices of Principia Mathematica, there does not exist a consistency proof for the system S. Hence, a consistency proof for the system S can be carried out only by means of modes of inference that are not formalized in the system S itself. Now, this is straight Gödel translated to English. This line here is misleading. He says here there does not exist a consistency proof for the system S. Right here, he starts talking about consistency proofs for the system S as if they could exist. Mathematicians don't normally make this kind of mistake. But Gödel strangely did. He should have said there does not exist a consistency proof for the system S within the system S. Hence, any consistency proof for arithmetic can be carried out only by means of modes of inference that are not formalized in arithmetic itself. And that makes it very clear. Now, if you're a person such as apparently Morris Klein, and this is all you see, then you would say, well, there's no consistency proof for, no proof of the consistency of arithmetic. Now, we mathematicians, we really love proof. We present to our students only things that have already been proved true, usually hundreds of years beforehand. And so we concentrate very much on things that have been proved. And if they've been proved false, well, we've usually proved those things. If something has not been proved true, nor has it yet been proved false, we call it an open question. So that there are infinitely many prime numbers is known because Euclid has an admirable proof there in the Elements. But there are twin primes like 29 and 31, 71 and 73, primes that differ from one another only by 2. There is huge heuristic evidence in favor of there being infinitely many twin primes. Scant, seemingly overwhelming, but it's not proof. And so we mathematicians will say that the infinitude of twin primes is an open question and will be closed only when somebody has a proof, not accumulation of heuristic argument, in favor of it. So this would appear that the consistency of arithmetic will remain forever an open question and will never be closed. But we see right in these 3 lines, oh, we can close it up, maybe, if we move to a middle language. And we'll see that's exactly what's going to happen here in this plot line. Now, to make sure that people have this straight, I presented here Joseph R. Schoenfield's statement of the same thing. The formula of Peano arithmetic, which states that Peano arithmetic is consistent, is not a theorem of Peano arithmetic. I've taken the liberty to restate that, making very clear the division between ground level mathematics and meta mathematics at every step. We have a meta theorem on ground level consistency proofs due to Gödel. The ground level statement in Peano arithmetic, which states the meta statement that Peano arithmetic is consistent, has no ground level proof in Peano arithmetic. There it is. Now, in my efforts to make sure we have this absolutely straight, here's my own way of stating it. The meta statement that Peano arithmetic is consistent can be translated to the ground language of arithmetic by a series of maneuvers requiring computer assistance in practice. This mind-bogglingly long and complicated ground level statement has never been proved. No statement of such complexity ever has been. But more than that, Gödel has shown that it is impossible for the ground level statement to have a ground level proof even in theory. Well, I've stated it 3 times. I hope you somehow understand this theorem. Let us move on. Here I have some comments. The meta-proof of the second incompleteness theorem is by a foldback argument, similar in spirit to the foldback arguments familiar to us mathematics professors in the proof of the irrationality of the square root of 2, in Russell's paradox, and in the non-denumerability of the continuum. Unfamiliar to us, even bewildering, is the huge complexity of the argument and constructions needed to prove the second incompleteness meta-theorem. I've seen even the Veritasium article does a pretty good job of getting the foldback argument across to a general public. However, the number of constructions needed to lay down the foundations for that foldback argument to occur is, as I say here, mind-boggling. It's just a huge amount of stuff needed to make happen, but then the foldback argument can be performed. Let's take a look at the implications of this second incompleteness theorem. Are we to conclude that arithmetic is inconsistent? Of course not. Even the first incompleteness theorem showed that what is true and what is ground level provable are not coextensive. Also, the meta-statement, arithmetic is consistent, and its ground level manifestation cannot be, in fact, the same thing. One is in a meta language, and the other is in the ground language. Are we to conclude from this that arithmetic might be inconsistent? Some have thought so, and as I was going beyond before, if you see only the first part of that slide, you'd come away with that impression. But both Gödel and Gentzen provided meta-proofs of the meta-statement, arithmetic is consistent. Schoenfeld presents Gödel's meta-proof and concludes, at the bottom of page 222 of his book, so piano or arithmetic is consistent. So there. We've got these authorities. You can go through all this, but we have meta-proofs, at least one, in fact two, that piano or arithmetic is consistent. Now, I've provided my own meta-proof of the consistency of arithmetic, and it works for me. Just appealing to authority, this might work. Could someone please hand me the abacus? Here's the meta-proof of consistency. We state it as a meta-theorem. Arithmetic is consistent. For, as proof, certainly 2 plus 2 being 5 is a false statement. We go out of the ground language of mathematics, putting this upside down, in fact. 2 plus 2 is not 5. Yes? Now, this is not in the ground level of mathematics, so already we've gone into a meta language. Also, the statements that make up the axioms of arithmetic are true. Those were the piano axioms of the last presentation. It has been shown that the rules of ground level proof preserve truth. From true statements, only further true statements can result from the rules of inference. These rules of inference are very basic, such as modus ponens, for those who know what that is, extremely basic rules of inference. Thus, there can be no ground level argument, no matter how long and complicated, from the true axioms of arithmetic through the valid rules of inference to end up with the false statement that 2 plus 2 is 5. Trivial proof by induction is suppressed. Those who know what that is would say, oh yeah. No argument, no matter how long and complicated, can go from true axioms through valid rules of inference and end up with falsehood. Thus, the false statement that 2 plus 2 is 5 has no ground level proof even in theory. Thus, by the reason for hope, arithmetic is consistent, which was to be demonstrated. For most people, the argument given above is adequate. And in fact, I think a lot of people kind of sense that 2 plus 2 can't be 5. How could it be proved to be 5? If you are such a person, you may now go home and sleep soundly tonight and know that the Golden Gate Bridge is not going to fall because 2 plus 2 ends up being 5 rather than 4 and so forth. But I've provided another one just for you to know. I found this in a book. It's a meta-theorem. It has to be conducted in a meta-language. That arithmetic is consistent. For assume, if possible, that arithmetic is not consistent. Then there is a ground level proof in that system of absolute falsehood. That's what it means to be inconsistent. And consequently, a proof of every ground level statement in arithmetic. If you can prove a false thing, you can prove anything. That was known even in the Middle Ages. by Gödel's first incompleteness theorem, let A be a ground level statement in arithmetic for which neither A nor its negation has a ground level proof. Thus, A and also not A both has a proof and does not have a proof. Oh, it has a proof because you're in an inconsistent system, and does not have a ground level proof by Gödel's first incompleteness theorem, which is impossible. Therefore, arithmetic is consistent, which was to be demonstrated. Now, I spent some time refuting assertions in the Veritasium article, Math's Fundamental Flaw, again saying how wonderful Veritasium is as a channel, with this one exception. So, mathematics certainly has a fatal flaw if arithmetic is inconsistent. Fatal flaws tend to let you know they are there. If you are programming a computer, your whole program will not compile if you have even one unbalanced parenthesis. There was an instance of dating to the 1970s or some such. The whole telephone system of the northeastern part of the United States just went down. Somebody put a break statement inside the code somewhere, and it was kind of like a go-to statement, and they altered the code and it went here rather than there. That one error brought the whole system down, and it remained down until somebody found that error. In chess, check is not checkmate. A beginning player may take his king being in check to be quite a scare. A beginning player may take his king being in check to be quite a scare. But a check in itself is nothing to be afraid of. In the same way, one may initially be alarmed by the fact that there is no proof of the consistency of arithmetic within arithmetic. But this concern, however serious, is allayed by the fact that there are proofs of the consistency of arithmetic outside arithmetic. Just as Gödel showed that maybe there could be in that slide in blue we had, it is. Gödel and both Gensen, and even myself, if you think, have provided these consistency proofs outside arithmetic. More refutations. There is a hole at the bottom of math. A hole that means we will never know everything with certainty. Surely we cannot know everything with certainty, but we can know some things with certainty. In fact, the vast bulk of our knowledge of conventional mathematics is known to a certainty that is the envy of every other discipline. You call this a hole? More refutation. Placing a question mark rather than an exclamation point on the consistency of arithmetic. At least this is better than the X that was in the prior version of the same episode. Once the incompleteness theorem is known correctly, together with the meta-proofs which have been provided on the issue, there simply is not much room for doubt about the consistency of arithmetic. More refutations. Cantor's work was just the latest blow to mathematics. This is the smoking gun. How I know that Veritasium article is founded on the work of this book of Morris Klein. That's straight out of Morris Klein. Neither Cantor's work nor the discovery of non-Euclidean geometry was any kind of blow to mathematics. It was good work, interesting work, unexpected work, and even controversial, at least in its own day. But it was not a blow to anything. As with the irrationality of the square root of 2, these results simply show how mathematics is even more rich and vast than had previously been thought. Oh, my word. I've got to refute it. I'm not going to let these things stand. The Veritasium article concludes, there will always be true statements that cannot be proven. And you might think that this realization would have driven mathematicians mad and led to the disintegration of the entire mathematical enterprise. Whoa! What if someone said, Lucretius had it right in his work De Rerum Natura? The universe does not have an end and cannot have an end. I'll suppress the argument Lucretius gives, but it looks pretty convincing. Would anyone worry that this realization might drive astronomers mad and lead to the disintegration of astronomy? Would astronomers say, well, since we cannot observe everything, we will not observe anything? It's all in the attitude. Do you want to dwell entirely on the negative, or do you want also to look around at what is positive? Look at these tremendous results in the coming slides. Each result was earth-shaking in its own time. Each result was proved by a foldback argument. And each result caused grave concern in its own day. And each result causes no working mathematician to lose sleep today. Let's look at them. The irrationality of the square root of 2. The Morris-Klein magisterial history tells us that there's a legend that the Pythagorean Brotherhood so disliked this result that the person who found it and proved it was thrown overboard. That's how much people can dislike these negative results. However, let's get to the mathematics. The irrationality of the square root of 2 on its face is negative. There do not exist integers whose ratio is exactly the square root of 2. So negative. Now look to the positive. There exist wonderfully good rational approximations to the square root of 2. Newton's method, set on finding the roots of the equation x squared minus 2 being 0, will produce approximations which double the number of digits of accuracy on each iteration. So if this algorithm's got it to 2 digits of accuracy, on the next iteration it will have 4 digits of accuracy, then 8 digits of accuracy, and 16 digits of accuracy, and 32 digits. Astoundingly efficient method of computation. And incidentally, all of these approximations are rational if you started off rational. Rational meaning, of course, the quotient of 2 integers. Back to earlier times. Once mathematicians proved that the square root of 2 is irrational, they could know that real numbers, as we call them now, are richer and vaster than anything that had previously been conceived. Before, people thought all numbers were the quotients of 2 integers. Once they found one that wasn't, mathematics expanded. Certainly did not go into chaos or contradiction or anything negative of the kind. We talk about the non-denumerability of the continuum for those who know what that is. One cannot create a bijection between the continuum of real numbers and the set of whole numbers. At least, one cannot do so in the ground language of mathematics. So negative. Now look to the positive. One can meta-create a set of concretely specifiable real numbers. Show that these concretely specifiable real numbers have all the properties you need to do all the mathematics you'd ever want, and denumerate them in a meta-language, associating each real number with its specification. If that is a bit much, let me ask, does any practicing mathematician of the current age lose sleep over the non-denumerability of the continuum? Again, we have Russell's paradox. One cannot form sets or statements with utterly wild abandon. So negative. Now look to the positive, what you can do. One can form sets with proper discipline in a graded fashion. And one can make statements about statements provided one interposes a division between ground and meta-languages. Set theory is fabulously richer now that it is practiced in a graded fashion, and mathematical logic got its modern start. Mathematics became richer, not poorer, as a result. And now, what about the incompleteness theorems? One cannot prove everything in the ground level language of arithmetic. One cannot ground level proof that arithmetic is consistent. So negative. Now we'll look to the positive. One can still ground level prove many, many results in mathematics. Our whole curriculum, our whole QA section in the library are of results, almost all of them, with ground level proofs. One can prove even more if one is willing to go into meta languages. One can prove the consistency of arithmetic in a meta language. Mathematics is richer than we currently know, richer than we will ever know, richer than we can ever know. I do not believe you can get more positive than that. This last part, following as a result of the incompleteness theorems, is what makes myself and many other people believe these incompleteness theorems are truly the greatest results in mathematics of all time. You can't know everything. Just get over it. The time has passed for any practicing philosopher or mathematician to view with fear or alarm either the first or the second of Gödel's incompleteness theorems. And as to the consistency of arithmetic, George Santayana said that doubt stimulates the mind, but only belief brings action. Those who doubt the consistency of arithmetic may be having the intellectual time of their lives, but we who actually do mathematics surely believe that our efforts are inside a consistent system. And we are fully justified in this belief. But still, there is room for disagreement. Perhaps Bill Watterson, in his great work, Calvin and Hobbes, said it best. Maybe I should have included it on my table of authorities. It's a little blurry. I'll read it for you. Here's Calvin, and a character is Hobbes. You know, I don't think math is a science. I think it's a religion. A religion? Yeah! All these equations are like miracles. I love that. Miracles. The mathematics department has more proofs for the existence of God than the whole rest of the campus put together, if you ask me. These equations are like miracles. You take two numbers, and when you add them, they magically become one new number. No one can say how it happens. You either believe it or you don't. And I don't know anything in all of math logic that can refute Calvin's argument right there, quite frankly. This whole book is full of things that have to be accepted on faith. It's a religion. And in the public schools, no less. Call a lawyer. As a math atheist, I should be excused from this. And with that, my presentation is ended.